All right, hello everyone. Welcome back to Physical Geology 1403. We're already starting in on a good conversation. Angel, that's right. Angel, which one do you prefer?
Which one? I like both.
You like both? All right, Angel. All right, Angel asked about normal rocks. A rock is at no time ever normal. Each rock was formed during a certain set of circumstances in the environment that it was formed. Okay? Those environments are hardly ever the exact same over and over again. Following similar themes, yes, limestones are often made in similar circumstances, but there are different types of limestones formed under slightly different circumstances. And no two are ever exactly the same. Two igneous rocks formed from two different magmas at two different periods of time will have different chemical compositions. Each rock tells a story, and that story unravels the history of our planet. And by understanding the history of our planet, we understand the history of every other planet, and therefore our universe unveils itself. Okay? So that's why I like to say that when you learn geology, you learn about our planet, but you're also learning about the universe itself. Okay? So hopefully by the end of my class, there will be no such thing to you as a normal rock. Okay? Thanks for bringing that up, though. Okay. Sebastian, would you mind grabbing that door for me? Thank you. All right. How's everyone feeling so far? It's perfectly natural if you're still feeling a little bit concerned about the class. Okay? Hopefully by the end of today, you'll have a better grasp of the expectations, in particular when it comes to lab. I will let you know right now, at the end of class today, you will get lab 1. Lab 1 is the longest lab. For one very specific reason, it discusses minerals, and minerals lay the groundwork, pardon the pun, for everything else that comes later. Okay, so that's why this is the longest lab. I want to make sure that you have that firm foundation so that everything that comes afterward makes sense. All right? Before we begin on today's content, do you have any questions for me? Anything at all? Nothing? Yes.
Can I hold this thing again?
Yeah, it can get passed around. You just got to go and just be gentle with it, right? If you have beef with whoever has it at the moment, just don't take it out on the snake. All right. Let me go ahead and bring this up here. Today we are learning about matter and minerals. Okay. Now, in our first lecture, in lecture 1, we talked about kind of a general overview of everything. Okay. We looked on the very large scale for the most part. Okay. We talked about plate tectonics. We talked about a little bit about volcanoes and earthquakes and stuff like that. Well, today we're going to narrow down on the tiny little detail, the smallest unit that builds this thing we call an Earth. Okay. Who can tell me what the smallest unit of existence is? An atom. Okay, if I said matter, someone tell me what matter is. What is matter? The proper answer to that is nothing. What's the matter with you? Sorry, I'm starting early today. Yeah. Okay, so can you repeat your original answer? Anything that takes up space. Okay. All right. It occupies some amount of existence, however you define existence. Okay. Any other definitions? Are we all cool with that? Anyone want to add anything to that definition? What was your name, by the way? What is it? Cuauhtemoc? Oh, cool name. Okay, where are you from? Here. And what's your major?
Business management.
Business management. Cool. You're at the right table. Isn't this my business table? You just naturally found your way to the business table. How about that? All my STEM people are over here, and this is the engineers in the middle, and my business people are off over there. It's just how it naturally fell, I guess. Okay. There might be an interesting social study in that somewhere. Luckily, I'm a geologist, not a psychologist, so I will not be doing that study. All right. This is great. Okay, so let's bring it back. Matter. Matter, someone else said atoms. Okay, atoms being that smallest unit of existence. Okay, but atoms themselves are made out of even smaller particles, namely protons, neutrons, and electrons. This is going to be your chemistry 101 really quick intro before we jump into minerals, okay? Because minerals are made using chemistry. So we'll talk about that here in a minute, okay? But you've got your protons and your neutrons, each of which combined make what is called the nucleus of your atom. Your electrons zip around on the outside, okay? Electrons traveling at about 1,360 miles per second. And they are tiny. They have the mass about 1/2000th that of a proton, which is already tiny by our standards, right? So you've got this nucleus, which is either a proton or protons and neutrons, depending on the element involved, and a whole bunch of electrons zipping around outside of it. Now, how do those electrons move? A lot of people are often taught that electrons just kind of orbit. They orbit, they follow the same path around a nucleus. I'm telling you today that is not accurate. This is not actually how they work, okay? It's more along the lines of this, where your electrons maintain a certain distance from that nucleus, but they are moving so fast and in so many random directions around that nucleus that they form what is referred to as an electron cloud, okay? And it is these electron clouds surrounding an atom that lend it, I guess you could call it, substance. The atoms that make my fingers, giving my fingers this solid state, okay? These bound atoms containing those electrons are interacting with the electrons of this table. This table is resisting me because its electrons and its shells and its electron clouds are resisting, pushing back against the ones in my fingers, okay? All right, just so we're clear as to how atoms appear. Now, some other things about atoms. There are a lot of them, and not all of them occur naturally. There are a substantial number of them which have actually been artificially made. Synthesized, okay? There are 94 natural and 24 synthesized elements that we know of as of the making of this video. That could change tomorrow. Someone else could cook up a totally new element in a lab somewhere, in a super collider out in Sweden, okay? It just has to exist for a picosecond, and you've made a new element. What I mean by exist for a picosecond? Well, some elements are what we refer to as unstable, okay? That is, they fall apart, some quicker than others. But as long as it exists for even just a picosecond, it will be a new element, okay? And there are 24 of those so far, all right? Now, how do we classify our elements? I'm going to tell you a little bit about that, but the first thing that you need to know right off the bat is that protons and neutrons and electrons have charges. Can any of you tell me what the charge of a proton is? Positive. And the charge of an electron? Negative. And the charge of a neutron? Hey, look at that. Good. Neutral. Okay. A proton and a neutron walk into a bar. The proton goes to reach for his wallet and says, hey, I think I lost my wallet. Neutron says, are you sure? The proton says, what? I'm positive. If anyone ever wants to give me the drum set there at any point while I do that, please feel free. Any of you know Porter Goodwin? Yeah? He was my drum guy last year. Okay. Now, because these subparticles that make atoms have a charge, the quantity of those particles in any given atom will determine what the overall net charge of that atom will be. Okay? We'll come back to that in just a moment. For now, though, you can see here we have a periodic table of elements, and I have a larger one here on the wall for your convenience, okay? Now, we organize elements on this table. It's not just random. They are in this orientation for a specific reason, okay? First of all, let's talk about the atomic number. It's this number at the top of each one of these boxes, like right there. Can anyone tell me what that atomic number represents? The number of protons in the nucleus. The number of protons contained in a nucleus is how we distinguish atoms from each other. If you increase or decrease the number of protons, what do I have? Another element. Okay, that's the first thing to remember. Okay, there are a few other things to remember here, which I'll get to in just a moment. This is just another way of a different, kind of a darker background if you have a hard time looking at light background periodic tables. Okay, now an atom on its own has certain properties, but atoms will often bond together. Okay, they will make these bonds, and there are multiple types of bonds that can form as a result of this. Okay, now what causes atoms to bond? Many of them will naturally just be drawn to each other for reasons I'll get into in a moment. But if you want to compel atoms to bond to each other, you often need to add or remove either heat or pressure. What does that do? It changes the environment that those atoms are in. If you change the environment, you will end up with different kinds of bonds that form. This is a principle that you will see applied in geology often, especially when we talk about metamorphic rocks here in a couple weeks. Okay? Now, there are three kinds of bonds: ionic bonds, covalent bonds, and metallic bonds. Why do elements bond together? Why do atoms bond together? In general, they are more stable in a bonded state. Why on earth would something choose to attach itself to something else? It's better that way in that circumstance. Okay? This is true of people. This is true of animals. There are animals that are parasitic off of other animals, right? Or that are symbiotic. Why do they do that? Because it is better for them to do so. They have better survival rates. That is a choice, either a conscious choice or one driven by instinct. As far as we know, atoms don't have either of those, choice or instinct. It is something that happens naturally because it is more stable in that state, in the environment that it's in. Now, it is perfectly possible, and this happens all the time, that say I add a little heat, I make some bonds. As soon as that heat is gone, those bonds break apart. Happens all the time. The opposite is also true. Can someone give me an example of taking heat away, making a bond, and adding heat, and then that bond breaking? Water. Bingo. You remove enough heat, and your water molecules will bond together even stronger than they were as a liquid. You add heat, and all of a sudden, they break back apart into the liquid. We'll come back to that example later. Okay? So, the octet rule states that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. Because does anyone remember what a valence electron is? The electrons on the outermost shell. Okay? That's the ones that if we could see them, we would see. We can't see anything below that, really, because the electrons on the outer shell are moving so fast. Okay? Those are the ones that interact with other atoms to make those bonds. Now, why 8? Can anyone tell me why 8? It's what? That's how much any atom can have on the outside ring? True, but why? I'm genuinely curious if any of you know the answer. I don't. As far as I know, no one does. Okay? It just is. It's a law of nature that 8 is the perfect number of valence electrons that an atom can contain. If it has 8, it doesn't want to bond. Now, we actually separate our periodic table into these columns based on the number of electrons in their outermost shell, in that valence shell. Notice, column 1, 2, let's skip the metals for now, 3, 4, 5, 6, 7, 8, okay? 8 columns. If you had to guess, tell me why all of these particular elements are in column 1. They have 1 valence electron. What about column 2? They have 2 valence electrons. Column 3, 4, 5, 6, 7, so on and so forth. What about column 8? They have 8 valence electrons. We call these what? Noble gases, typically. Okay? They are inert. They do not typically seek to bond with anything else. Why? Their octet rule is satisfied. Therefore, they are inert. We use those for a variety of things. Some interesting things. If you're ever transporting a volatile or electrically conductive material, oftentimes you will put it in a buffer of one of those gases because those gases will not interact with that substance and cause it to blow up or spark. Okay? They are not naturally prone to such things because they are inert. They are not seeking to bond with any other elements. Okay? So let's talk about these bonds. Okay? So our valent or ionic bond, as I called it before, that's when an electron is transferred. And then in a covalent bond, electrons are shared. And then in your metallic bond, all the electrons within that substance, that uniform substance, are shared between all the particles. Okay? Let's talk about each one of these, starting off with our ionic bonds. Okay? Now, let's go back to our discussion earlier about charges. If I have an atom with 2 protons, this is just theoretical, just for the sake of the exercise, 2 protons and 1 electron, what is my net charge? Positive. Why? 2 positive, 1 negative. My net charge is positive. Okay? If I have 1 proton and 3 electrons, what's my net charge? Negative, plus 2, or negative 2, right? It's a 2 negative. Okay? Perfect. All right, so we're familiar with this concept. It's pretty basic. So what happens if I have an element that has it has a positive charge with 1 valent electron, and an element with a negative charge and 7 valent electrons? Why would they join? They each want 8. So you've got you've got an atom that requires 1 and an atom that requires 7 to be happy. And what are they going to do? They're going to bond. Where is sodium on my periodic table of elements? Column 1, meaning it has 1 valence electron. Where is chlorine? Column 7, meaning it has 7 valence electrons. Do you think they would like each other? Yes! Add to that the fact that chlorine has a net negative charge and sodium has a net positive charge. Boom, bada boom. You end up with sodium chloride. What do we call that? Salt. An extremely common bond on our planet. Okay? Salts. Sodium chloride. Positive and negative attract each other, just like a magnet. You ever held a magnet, 2 magnets, and they were drawn to each other, and then you flipped one over, and they were repelled from each other? Okay. It is the opposite charges that attract each other. Opposites attract, and just like that, I saved you all a whole bunch of money in relationship therapy later on in life. Okay? Opposites attract. Accept that. It's a law of nature. Okay. So this is an ionic bond. Our sodium is lending its 1 valence electron to our chlorine. And that's its kind of entry payment, I guess you could say, for having given its one valent electron to the chlorine, it gets to hang out and enjoy the benefits of those 8 electrons. And that's our sodium chloride bond. That is an ionic bond. In a covalent bond, electrons are shared. So a simple example of this would be if I had 2 hydrogens. I have a proton and an electron, and these 2 hydrogens approach each other. All of a sudden, the electron of each is equally drawn to the proton of the other as much as it is itself. And so you end up having 2 protons here with 2 electrons. They're kind of sharing both nuclei, doing this, going back and forth. Okay? This is a covalent bond. And then in a metallic bond, your electrons are shared. This is a very cool aspect of metals. What do we call it when a substance can transfer electrons freely through it? Conduction. Bingo. This is why we use metals as conductors. This is why you never, ever, ever walk outside in a lightning storm holding a metal rod, right? Don't do it. I'm looking at you. Don't do it, okay? Why? You're going to get struck by lightning. Electricity, first of all, being drawn to the charge of that metal. And then also, you're holding the metal. So that electricity is going to transfer. It's going to conduct through that metal because of this simple fact that in metals, electrons can travel freely through the substance. Electricity, that's just electrons. That blue snap when you plug in your toaster or you pull out your hairdryer, right? That's electricity. You are looking at electrons, trillions of electrons in that split second that you saw that blue snap, trillions of electrons you saw there, okay? That's going to travel through that metal pole and into your body and deep fry you crispy, okay? It'd be cool for everyone else. You probably wouldn't feel it for long. Anyways, a cool story other people would get to tell. Only a few people have ever survived being struck by lightning. Far more people die, okay? And that's only because, by the way, the only reason why anyone survives being struck by lightning is if that electricity can also, bless you, transfer through you and into something else like the ground. Okay? So if you're like wearing rubber shoes, you're dead because it can't transfer out of your body. But if you're like barefoot on the ground or on some other conductive material, when it enters you, it can conduct through your body. It'll still mess you up, but that's how people survive. Steel-toed boots? Yeah, sure. Anyways, so gold, silver, copper, these are some of the best conductors on our planet, okay? And the reason why these things are more and more expensive all the time. We use gold as a conductor in our most important infrastructure. If you were to strip the wiring out of, say, an Apache attack helicopter, you would find a lot of gold wiring in that. Why? Because it's the best conductor we've got, okay? And they don't want to risk a $250 million piece of equipment crashing because of an electrical malfunction, right? You and I, we've got copper in our houses. That's the cheaper of the options, but still getting pretty expensive for reasons we'll talk about when we learn about mining later, okay? Now, that's ions. Any questions about ions or bonds or anything like that? No? Okay, then let's move on. Let's talk about radioactivity. Now, the mass of an atom is this number right here, underneath of the letter, okay? Who can tell me what the mass represents? Right, it's the mass of that atom, but Okay, let me put this question another way. What part of the atom represents the vast majority of that mass? The nucleus, right? That nucleus is going to be far and away most of that mass. Any mass contained in the electrons is why it goes out to like 4 decimal places on some of these, okay? It's tiny. Remember, an electron is 1/2000th the mass of a proton, right? Almost negligible. But for some of these, there's enough electrons that it actually manifests on the mass. But for the most part, it is the nucleus itself, okay? So if I were to ask you, here we have potassium. How many protons does it have? What's its atomic number? 19. Therefore, how many protons? 19. Okay, but its atomic mass is 39. So how many neutrons do I probably have in my nucleus? You just throwing out numbers for fun?
No. Because the atomic mass minus the amount of protons.
Uh-huh. Which is what?
I can't really see it.
20. 39 is the total mass. 19 of those are protons. Therefore, how many are left to be neutrons? 20. There's 20 neutrons in that nucleus along with 19 protons. That gives me a mass of 39, give or take the electrons. Okay? So, what happens if I slurp away an electron for one reason or another? What do I now have? No. No. I'm pulling an electron. What happens when I remove an electron? I change the, well, I mean, yes, but almost insubstantially. Huh? The charge. I have taken away a negative charge. I have changed that, possibly creating a ion. Remember, an ion is a charged particle, positive or negative. If I remove a negative electron, I am probably creating a net positive charge for that atom, right? If I add an electron, I'm adding a negative charge. In either case, I'm changing the charge. I'm giving it a charge. It is no longer neutral. Therefore, it is an ion. What happens if I slurp away a proton? What do I have? Proton.
Another element.
A different element, exactly. Add or subtract electrons, I get an ion. Add or subtract protons, I get a different element. Now I'm going to slurp away a neutron. What do I have? Here we go. All right, I have taken away a neutron. I have changed what? The mass. I haven't changed this. I haven't changed the charge. I've changed the mass. This gives me what is called an isotope. That's the word you were looking for. An isotope. An isotope is an atom that has different mass than the standard version of that element. For example, potassium here, good old K, right, has a mass of 39. If I take away a neutron, it will be at 38. I now have an isotope of potassium. Are you following me here? Good. Now, some elements don't really care. Carbon, for example. Where's carbon on my periodic table of elements? I'm hearing 4, I'm hearing 6. Explain. Where do you say 4?
I can't. You see carbon, the C?
Yes.
Because it has like 4 covalent.
It's in column 4. Okay, thank you. It's in column 4, meaning it has 4 valence electrons. Okay, but what's its atomic number? 6, meaning it has 6 protons. Okay, but what is its mass? Can you tell them all what that says? 12. Okay, so we've got carbon 12. Carbon 12 is the standard vanilla Plain Jane version of carbon. Carbon-12, 6 protons, 6 neutrons. However, there exists an isotope called carbon-13. Someone tell me what carbon-13 would have. How many protons?
7.
Ah, but if it has 7 protons, isn't it nitrogen? So carbon-13 must have what? An extra neutron. Still 6 protons, but now 7 neutrons. You can change the neutrons without changing the element. It does, however, make it an isotope. Carbon-13 has 1 more proton. It has grabbed the proton and brought it into itself. 1 more than your normal plain carbon will. Then there's carbon-14, which has what? 2 more neutrons. Okay. You can actually use the ratio of carbon-12 to carbon-13 in organic material like a tree to figure out temperature and precipitation rates over time as long as that tree was alive. That's what my entire master's degree was on, except I used microfossils of tiny crustaceans in freshwater, not trees. Okay, same principle though. Okay, so like I made an entire environmental reconstruction for an area in Eastern Oregon using the carbon-12 and carbon-13 ratios in those fossils. They're very useful. We love isotopes in paleontology. Okay, carbon-14 is very interesting. Carbon-14 is an isotope that is only released through burning fossil fuels. So if you were to look at the record of carbon-14 that we can track by analyzing, say, trees and whatnot, fossils, then you would see very little carbon-14, pretty much just from the occasional tar fire, or if a coal bed lights on, is like struck by lightning, right? And then all of a sudden, industrial revolution, whoop, carbon-14 skyrockets. Your bones? No, your bones aren't made out of wood.
Oh, I thought it was fossil.
Yeah, fossil fuels. So anything that's hydrocarbon based, okay? We'll talk more about how those are made later, but no, burning your bones shouldn't release any carbon-14. Okay? You do have carbon in your bones. You have a lot more other stuff, but there is some carbon in there, all right? Okay, now those are, some of these are stable and some of them are unstable. Carbon-14 will break down, okay? Carbon-12, carbon-13, those are pretty dang stable. You ever heard the term carbon dating? Okay, people will often use that term erroneously, actually. The carbon dating is what they'll describe as, okay, so we carbon dated this thing, we found out it's 240 million years old. That's actually inaccurate. Carbon dating using carbon isotopes can actually only go back about 10,000 years or so before it starts getting really inaccurate. So when people say carbon dating for anything longer than 10,000 years, they're usually referring to using other isotopes, isotopes with longer lives, which I'll get to in a moment, okay? But they say carbon dating because it's shorter than the actual name, which is laser ablation multi-collectively coupled plasma mass spectrometry. You can see why they just call it all carbon dating. Okay? But what about our unstable isotopes? The ones that don't like having extra neutrons or neutrons removed. What happens to those? They're unstable, and therefore they will do what? When something in nature is unstable, it's going to change. This is a principle of nature. If something is unstable, it's not just going to stay there. It's going to change to become more stable. Remember that. It's an important principle here. How does it change? How could an element that is unstable, it doesn't like its current configuration of particles, how would it possibly change to become more stable? Not bonding. Good idea, though.
Making another element.
How would it make another element?
By joining, release
The opposite. Releasing what?
proton.
Ah, there it is. It's going to blast particles off of itself. It's going to remove protons and neutrons and electrons until it reaches a new stable condition. We call that a daughter isotope. So you start off with a parent isotope, usually unstable, okay? And then eventually, after some period of time, you will end up with the stable daughter isotope. Classic example, uranium. Uranium-235. Where is uranium here? Someone tell me where uranium is. Someone tell me the number. How about that? What is its atomic number?
86.
No.
92.
92. Uranium, 92. Okay? Meaning it has 92 protons, but its mass is what? 238. Normal, vanilla, plain Jane uranium is a mass of 238. We use uranium-235 in our reactors, in our nuclear reactors. What is the difference? How many neutrons are different? 3. There are 3 less in the unstable uranium isotopes that we use than there are in the normal natural version. Okay, these are all natural, but you know, the normal version of uranium will have 238, the stable version. Okay, so basically, if we just strip some neutrons away from uranium, it will become an unstable isotope. It becomes what we call radioactive. Radioactivity is when an unstable isotope is blasting those particles off itself. It's sending protons and neutrons and electrons in every direction. That's radiation, folks. You ever felt radiation? Yeah, I was going to say, all of you have. You stepped outside, presumably. Unless you were born and lived your entire lives inside this building, you have felt radiation from the sun. Okay? That heat you feel from the sun is radiation hitting you from the incredible number of fission and fusion reactions going on in our sun. All that distance away, it makes it here and hits your skin, and that's radiation. However, if you are ever closer to a source of radiation like uranium-235, that's when you start getting radiation sickness. Okay? And if you ever gotten a really bad sunburn, like so bad your skin turned purple and your skin peeled off? Huh? Yeah, it's often called sun poisoning. It's a really bad case of radiation poisoning. It's actually killed the cells in your sun. Wow, in your skin. Okay? Believe me, there are much worse forms of radiation poisoning. Yes. Yes, your skin cells die and then your body sheds them off. That's why multiple layers of skin come off whenever you get a really bad sunburn. You're trying to get rid of the cells that have been killed or mutated by the radiation. We'll talk about mutation in 1404. I don't really go into that in this class too much. Now, we have found out really cool ways to use radioactive isotopes. We can use them for dating objects, okay? I can figure out how many of the total quantity of uranium in an object has decomposed basically into its stable version. Uranium-235 ultimately would become lead-207. Okay, stable lead. If I figure out the ratio of uranium to lead, then I know how old that object is because I can do the math backwards. Uranium takes about 750 million years. So by calculating how much, if I have a 50-50 split between uranium-235 and lead-207, I know that that object is 750 million years old. Because since that rock was made, since that uranium was incorporated into it, let's call it an igneous rock just for easiness here, okay? I know that rock is at least 750 million years old because the ratio of unstable to stable isotopes is 50-50. That means one half-life has passed. That's the amount of time it takes for half of the radioactive isotope to decay into the daughter isotope. Why do we go in half-lives to measure this? How many? You all right over there? How many times can you cut something in half before you run out of it? Infinite. Yeah, infinite. And so we use half-lives because that gives us a metric by which we can continually count the number of half-lives that have passed and therefore figure out exactly how old a thing is. That's radiometric dating. I mean, you could do it in quarter lives, but why complicate it? Half-lives. I mean, it's it's not always perfect, right? Let's say there's a 73-27 split, then yeah, you got to do that math, right? But a half-life, where you continually chop the remaining amount in half, that's just the standard, okay? So, what's another use that we have figured out for radioactive isotopes? Reactors, right? We already talked about that, yeah? Yeah, reactors. Okay, what's another use? Right. There's another way we figured out how to use these things. It's a nuclear weapon. Well, let's talk about that. Okay, so if I take those uranium-235 isotopes that are blasting radiation out, and over the course of 750 million years, half of that is going to have decayed to be stable. What happens if I figure out a way to release all that energy at once? What happens if I split that atom and all that pent-up, unstable energy is just released? We get a kaboom. That's a nuclear weapon. Any of y'all ever see Oppenheimer? Yeah? Great movie. Fantastic. Okay. When they figured out how to split that atom and they made that first nuclear weapon, it horrified most of them so much that they didn't want anyone to know about it. But the government paid for it, and so they knew it existed, and the cat was out of the bag. Most of the scientists realized what they had done and were like, oh, crap. And then only 10 years later, every major nation on Earth had nuclear weapons. And then a short time after that, we entered the Cold War. You familiar with the Cold War? Yes. The Cold War was essentially Western ideology versus Eastern ideology. America and its allies and our capitalist free market values versus Eastern ideology, which had communism and socialism and all of that going for it, okay? Mostly it was America and Russia that were in this big standoff, the two largest nuclear powers on the planet. Yeah, I'd prefer it if he stayed on the table. He'll be gone like that if we don't watch him close enough. Where was I? Cold War. Okay, and that lasted for decades. Okay, and it only grew and grew in tension as each side continually made bigger and bigger bombs. It reached a point that was so bad that Russia developed something called the Tsar Bomba. You ever heard of this? Tsar Bomba, the largest nuclear weapon ever tested. Where's oh no, here's my stick. Okay. This roughly banana-shaped island above Russia right there, see that right there? That's where they tested the Tsar Bomba. An explosion so powerful, it shattered windows across Europe and was felt on earthquake detectors, seismometers, on the entire planet. Yes. A weapon so powerful that it would only take probably 5 of them to completely cripple the United States. A couple on the East Coast, a couple on the West Coast. That's it. We'd be done. Now, because of the effect that it had, they couldn't hide this. The entire world knew that they had it because of what it did, right? It was sensed everywhere. It broke all those windows. And by the way, it rendered a substantial part of the island uninhabitable for a couple thousand years, okay? It was so powerful that an international group of countries came together and outlawed weapons that powerful. They straight up said, no one should have any power like this. This will wipe out the human race if it ever comes to war. The smaller nuclear weapons, they're bad enough. They can destroy a city. You drop a couple of those and, you know, the entirety of the East Coast of the United States is just gone. That's too much. We can't allow that. And so the international community banned them. But you know everyone still has them, right? No one's going to take the chance that they are the one group that doesn't. Yeah. Sorry, say that again.
Didn't it work like the Castle Bravo would be long?
The Castle what?
Castle Bravo, is that what
Castle Bravo. Oh, you're talking about another nuclear test? Yes, this was the largest nuclear test ever conducted. Above ground. We still don't know exactly what all goes down underground. Most nuclear testing happens underground these days. Okay. But yeah, isotopes, radioactivity, fun. Yes, destruction. Any questions about anything we've talked about so far? Yes.
You said it was like it was called the
SAR bomba. TSARBOMBA. SAR bomba. Yeah. Pretty significant.
Was that one also made out like with uranium, or was that one made with hydrogen?
No, that was a hydrogen bomb. Right. Let me mention this. A standard nuclear weapon releases energy when you split an unstable isotope. Imagine how much more energy you would release by splitting a stable isotope. And that's what a hydrogen weapon is. You take a stable hydrogen and you split that sucker. It's not in an unstable state. It has not released energy up to this point. It's still full-on quantum, however much energy it can hold. The amount of energy held inside of the most simple atom, a hydrogen, is an incredible amount of energy. It's amazing how much energy can be held in such a small unit. But when you split that unit, that's what gets you a hydrogen bomb. Can we do a lab where we split one? How much do you like Texas? Not that much? You say Puerto Rico?
Yeah.
Yeah? Okay. You set off a hydrogen bomb here. Puerto Rico is going to have a problem too. Sorry. They can have a problem too? Wow, you just like to watch the world burn, huh? You're one of them. All right. I see. It's good to know where you stand. All right. Any other questions? No? All right. Well then, let's transition into talking about what a mineral actually is. Okay. Now, there are many definitions for the word mineral. You may have heard them used in, say, medical terms before. Drink this. It has lots of good minerals for you. What they usually mean there are vitamins. Okay? Those words are often used interchangeably in the medical industry. In the mining industry, yes, sir. Are you done? Yeah, you can pass them off. There's usually someone else that wants them. In the mining industry, a mineral is any substance that you can get out of the ground for monetary value. That includes oil and gas. Those are considered mineral resources to the mining industry. As far as I am concerned in geology, as just a geologist, and as far as you are concerned in my class, there is one correct definition for a mineral. And this is that second thing that I will require you to know word for word. We had what did we have last time? The principle of uniformitarianism that you needed to know word for word. This time, it's this. The definition of a mineral is any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Whew, what a mouthful. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. All right, let's talk about that now. Because someone, let's see. How about this? I'll just jump straight to it. Let's debate. Is ice a mineral? Who says yes? Who says no? Okay, we got some no's. You say yes? You like playing devil's advocate, don't you? I like it. Okay, well, let's talk about it. Is ice naturally occurring? Is it inorganic? Is it a solid? Yes. Does it possess an orderly crystalline structure? Does it have a chemical formula? Yeah, H2O. According to our definition, is ice therefore a mineral? What? Yes, ice, as a matter of fact, is considered a mineral. It is an oxide mineral, which is why the study of glaciers falls under the general overview of geology. Yeah, that's why we have an entire lecture on glaciers coming up in Module 2. How about that? Ice is a mineral. Think about that the next time you drop them in your drinks. Okay? Now, what's the difference between a mineral and a rock? I touched on this last time, but let me just go over it again. No. But I appreciate the enthusiasm that you just jumped right in with an answer. They do have a chemical formula. Here's the difference. A mineral is not a rock, but a rock is made of minerals. A mineral is this definition. A rock is a bunch of those that have formed a larger substance. Let me give you an example that at 10:30 you will not appreciate very well, okay? Chocolate chip cookies, okay? I am going to make some chocolate chip cookies. Jocelyn, help me out here. What do I need for chocolate chip cookies? Flour, chocolate chips, eggs, butter or oil or Crisco or something, yeah, okay. Right, receptacle, maybe some salt, baking soda, vanilla, right? I enjoy them with almond extract. It's surprisingly delicious, right? Okay, also cheesecake made with almond extract. I'll have to take your word for it. I don't drink coffee. Okay, now, we have all these ingredients here on this table to make a chocolate chip cookie. If I grabbed a chocolate chip and I handed it to you and I said, here, take a look at this chocolate chip cookie, you'd look at me like I was crazy, right? That's not a chocolate chip cookie. That's a chocolate chip. You said you were giving me a cookie. That's exactly the same thing with minerals and rocks. If you handed me this mineral and said, here, have a rock, I look at you like, that's not a rock. That's a mineral. You promised me a chocolate chip cookie, but you gave me a chocolate chip. You following me? Minerals are the ingredients of rocks. Just like if I had a little pile of flour or salt in my hand and I said, here, have a chocolate chip cookie, you'd never trust me again, right? Okay, so let's use the proper terminology here from here on out, okay? Mineral, rock, okay? Some of this is in this, but this is not that. Following me? Perfect. All right. Now, minerals themselves have properties, okay? And it is these properties that you are going to learn to identify them with. We're going to have so much fun. Okay, so some of these properties, optical properties, that is how the mineral appears to you, okay? This includes things like its external appearance, like how shiny is it? Does it look metallic? Does it look submetallic? Does it look oily? Does it look dirty? Does it look like glass? Does it look glassy, right? Things like that. Also, how translucent is it? Does light pass through it? Can I see an image through it? All of that. Those are all optical properties. Then you've got your crystal shape. Okay? Your crystals, because they are essentially repeating patterns of chemical bonds that have formed a solid, they are going to often make geometric shapes. Yeah, they're going to make shapes naturally. And you're going to identify those shapes using some materials that I give you. Okay? Then you've got the strength. We use this by testing the hardness. Okay? You test the hardness of a mineral using common household objects. Now, there is no number scale, so to speak, for hardness. We use them based on relative hardness. Okay? Is it harder than or softer than, say, glass or another mineral? So we have a scale of 1 through 10, with 1, the softest, being talc. That's the same mineral that you crush up to make baby powder, if anyone's interested in that, okay? Then on the top, we've got diamond at 10, for obvious reasons that I'm sure we're all familiar with because it's pretty ingrained in our culture, right? As hard as a diamond, right? Now, in each of your test kits in front of you, and for those of you watching this online, watching the lab videos, you're going to see that there are glass plates. Come on, camera. Stay with me here. There we go. There are going to be glass plates. Glass falls right here, 5.5 on our Mohs scale of hardness. This is the MOHS, Mohs scale of hardness. You each have a glass plate in there that you're going to be testing your minerals with to determine the hardness. Now, I don't expect a number 1 through 10 on this because I only give you the 1 point of reference, glass. You do need to tell me, though, if your mineral is greater than or less than the hardness of glass. If it scratches the glass, it's what? Greater than 5.5. If it doesn't scratch the glass, it is less than 5.5. That's how you'll be finding the relative hardness here. I can only give you that 1 frame of reference. There are test kits that do have all of these, 1 through 10, but they're very expensive, and I don't have that kind of budget. So here we are with glass, all right? Then there are a few other things. There's density, but we won't be testing density in this class. It's not necessary. We're all familiar with what density. Do you have a question? Oh, okay. I thought. We're all familiar with what density is. We talked about it last time. Measure of mass per unit volume. How much stuff you have in a certain space. Okay. There are ways we can test that, but it's not essential for our class here. Things like taste. You can, in fact, taste minerals. Yeah. Okay. However, and this is very important, please, please, please do not taste numbers 18 or 37 in the back, okay? All of those minerals and rocks in those black trays back there, those are your practice set. That is your baseline. Those are what you are going to be identifying. Well, you're going to be identifying through in sets that I give you, but those are what they all could be. There are 51 practice set minerals for Lab 1. You need to identify 24, and they're going to be random out of those 51, okay? But back there, please do not taste box 18 or box 37. If you do, and you forget, and you do, please tell me so I can contact poison control. One is a lead sulfide, and one is an arsenic, okay? So none of that. Deal? No one goes to see a nurse today. Please remember. Okay. You wouldn't die, and you probably wouldn't even get sick. But because they are toxic, I still need to report it. Because if something did happen to you and I didn't report it, that's me out of a job and Odessa College sued. Okay? So we still need to, yes. Has it happened to me before? No. No one's ever done that. I still really emphasize it, though, because I never want it to happen. You can feel free to touch them and hold them and look at them, just as long as you don't ingest any of it. I would even encourage you to wash your hands over there at the sink after you touch them, just to make sure there's no secondhand contamination, like if you go and have lunch right after this. You can smell it. Yeah, just don't lick it. And I will tell you, there are a few over there that it may, in fact, be beneficial to lick. I will tell you that there are 2 in particular that look very similar. And one of the best ways to tell them apart is a little taste test. Yeah. Okay. Now, just be wise there. If you have any doubts, if you say, hey, is this one that's safe? Please just ask me. Okay. Then there's the texture. When you feel it in your hand, how does it feel? Right? These are things that we're not exactly going to be testing. I don't have a test taste on the lab. I don't have a texture test on the lab. There's no density test on the lab. There's no smell test on the lab. Yes, some of them have a distinct scent. That big yellow rock over there by the map, that's sulfur. It smells like rotten eggs. You couldn't smell it? You might want to get your smeller checked. Just kidding. It is an older sample. I might need to crack a little piece off to let y'all smell it. And then there's effervescence. Effervescence is an effect that happens when you drop hydrochloric acid on some minerals. There's a little bottle in each of your test kits. That is not water. Do not drink it. It is hydrochloric acid. Matter of fact, please do not even get it on your clothing. Hydrochloric acid likes to eat clothing. It will dissolve the fibers in your clothing, and you'll end up with holes. I can't tell you how many shirts. Look, you can even see, I've got a few in this shirt. Just little drops have gotten on so many of my shirts that like I've got holes showing up in them because it just dissolves the fibers. My wife hates it. I go through so many shirts, right? So just exercise some common sense and restraint. Please know they're not little squirt guns, okay? Don't be doing that at each other, all right? If it gets on your fingers, that's okay. It's not going to hurt you. I've diluted this. It's not strong enough to actually hurt you. It may feel a little slick on your fingers. It's just dissolving that top layer of skin, which is dead already anyway. So don't worry about it, okay? That's why it will feel a little bit slick. But what you're doing here is there are some minerals that will react. They will have this bubbling effect, this effervescence. One will react very strongly like this, and one you will need to kind of powder it a little bit on the table and drop some acid there on the pile of powder for it to react. Okay? All right, cool. So these are your properties. Let's talk about each one in a little bit more detail. Your optical properties, this includes luster. That is your outward appearance of your mineral. If I were to try and describe a mineral by its luster, I may describe it as metallic. It's got that kind of shiny, metal-looking appearance, right? Like it's pretty obvious if something looks like metal. You're all familiar with what metal looks like, right? I shouldn't really need to explain that. Same thing with glassy. If it looks like it's some kind of colored or clear glass. Yeah, like an amethyst appears very glassy, right? Another word for glassy, by the way, is vitreous. Okay, some of the resources I give you may use the word vitreous instead of glassy. They are interchangeable. You can use either. Okay. Then there's things like earthy. If it looks like it's like compacted mud or dirt or something, that's an earthy luster. Or oily, if it looks like you sprayed it with baking spray or something like Pam, right? It will appear greasy or oily. Then there's pearly. If you guys have ever seen mother of pearl, like the inside of a seashell, that's a pearly luster. Okay, so really you don't even have to stick to those ones. You can give me a word that works for what you are seeing. As long as it is a one-word description of the luster, that's what matters to me. It doesn't necessarily have to be these, as long as it makes sense, you know? Don't make up a word either, all right? All right, then you've got your translucence. If it is opaque, no light will go through it at all. If it is translucent, light will go through, but no image. And if it's transparent, light and an image can go through, like glass, okay? And then there's the color. Now, I want to issue you all a very, very important word of warning here. Do not put too much stock into color. Color is one of the least valuable methods of identifying a mineral that there is, okay? I still want you to record it. There's a place in the lab for you to record color, but don't put too much stock in it. Why might that be? The same mineral can occur with different colors. Like amethyst. Amethyst is quartz. It is quartz. Quartz, quartz. Amethyst is just purple quartz. Why is it purple? It's got some iron in it. That's it. Otherwise, the same mineral. Okay? I think my camera's stuck again. Come on, stay with me here. There we go. Okay. Also, two different minerals can be the exact same color. They will have different cleavage, different crystal form. They'll have different chemical properties, but they may very well show up as having the same color. Don't let the color distract you. At best, we use it as a tiebreaker. Okay? If it's this or this, but this one definitely never shows up as purple, then you know it's got to be that one, right? Okay. Streak. Each of you in your test kit, and those of you watching the lab videos online, you will see that there is a white porcelain plate. There's also a black porcelain plate, okay, in those test kits. and you take a mineral and you scratch it on there, just put a little bit of elbow into it. Don't, just put a little elbow into it. Try and make it streak a little bit off there. Why? Because it will show you a little bit more about what maybe the true color of that mineral is. What you're looking at on the outside may in fact just be the effect of oxidization. This mineral appears golden on the outside, but the streak is black. Okay, so that gives you a little bit more because you're looking at a layer of that mineral that's only a few atoms thick on that white porcelain and that black porcelain. If you scratch it on the white and you can't see anything, scratch it on the black. You may be looking at a white streak on a white plate. That's why I give you both. Okay? Then there's your crystal shape, also known as your crystal habit, also known as your crystal form. Okay? Those are interchangeable. Okay? So they show up in all sorts of different shapes. Just a few examples. Octahedrons. Okay, this kind of pyramid on pyramid sort of shape. That's an octahedron. Dodecahedrons. The jewel stone garnet shows up like this naturally. These were not cut. This is how garnet naturally grows. I have a few of them up here if you want to take a look later. Okay. And then there are halite cubes. It naturally forms into cube shapes. By the way, halite is the mineral name for salt. Salt makes cubes. Naturally, that's how it grows. That's also how it breaks. It will make these cubic shapes. Yeah. Bismuth? I don't know that bismuth has a distinct shape. There are bismuth-rich ores. I don't know. Talk about that one later. Good question. I'll have to look that up probably. That's another thing, by the way. If I don't know something, I'm not going to make it up. I'm going to straight up tell you I don't know, and we're going to find out. Probably not right now, though, because I'm recording, but later. All right? Okay. Tenacity. That is how a mineral breaks. Okay? We already talked about hardness, which is how hard it is relative to other minerals, but how does it break? Does it splinter? Does it shatter? Does it bend and then flex back? Does it bend and then keep that shape? Okay, that's tenacity. So if it's brittle, it will shatter. If it's malleable, it will bend and then retain that shape. If it's sectile, it will split into shavings or splinter like wood. If it's elastic, it can bend and then return to its original shape. Okay? That's tenacity. Then you've got hardness, which we already talked about, your Mohs scale of hardness. You'll just scratch your minerals on glass to figure out what you got, greater than 5.5 or less than 5.5. PSA here, please keep the glass and your streak plates also flat on the table when you are scratching them. For two reasons. Number one, safety. Glass can break, and if it breaks in your hand, you might get cut. All right? Also, because we have black tabletops here, it is far easier to see if there is a scratch on the transparent glass against the black background than it would be on the background of your hand. Okay? So it's practical and safer to just keep them flat on the tabletops. Any questions so far? Good. Makes sense. Good. You know what doesn't make sense? A penny. It makes 1 cent. Thank you. All right. Okay. Let's talk about mineral cleavage. And I am going to warn you that this is probably going to be a little bit difficult to get at first. This is probably the property that people struggle with the most at the beginning and then catch on later on. Okay? Do your best and ask me the questions that you need to ask. All right? Cleavage is the manner in which a mineral will break based upon its internal atomic structure. Back up here and remind you about the chemistry we learned earlier. Bonds are formed when two atoms are drawn to each other electrically. When two atoms bond, and then a third atom bonds, and then a fourth atom bonds, and then so on and so forth, you are going to end up getting a repeating pattern of that same atomic bond that forms the solid structure of your mineral. It's just the exact same bonds happening over and over and over throughout that entire mineral. That's what makes a mineral a mineral. It is a repeating pattern of the same bonds, and those bonds are unique to those minerals. Okay? For example, ice. Ice is H2O. What mineral also has the atomic bond, the chemical composition H2O? It's not a mineral, though, is it? It's not solid. Right. Nothing. H2O in its solid form is only ice. It's the same for every other mineral. Their chemical compositions are unique. The same pattern repeating over and over throughout the entire structure. So let's say that I've got a mineral that has one bond that is not as strong as another bond. If I exert stress on that mineral, which bond is going to break first? The least strong one, right? Your mineral is going to break along that bond first. And since it's a repeating pattern of the same bonds through the entire structure of the mineral, your mineral is going to crack and break along that same plane. That one plane in your mineral, along which all those bonds exist, the weaker bonds, it's going to break there. And that, my friends, is cleavage. Mineral cleavage. The manner in which a mineral breaks based upon its internal atomic structure. Now, 2 years ago, when I tried teaching this, it was extremely difficult for students to comprehend because I had no actual physical models to demonstrate with. So I spent the summer and I designed my own and I 3D printed them, and I have a patent pending on these because no one else has done this. But I designed these. They've got little magnets in them so that they just stick together until I break them apart along cleavage planes. And I have an example of these for each type of cleavage that you will encounter in my class. So if a mineral has one plane of cleavage, it is going to break in a flat plane in, you guessed it, one direction. It's just going to break like this. And so you'll often end up with what looks like book leaves, like book pages of a book that are splitting off of themselves in that mineral. One plane of cleavage. With two planes of cleavage, it gets a little more complicated because now we are not only dealing with, I guess I need to reglue this magnet. We are not only dealing with how many, we are now dealing with how many planes of cleavage are there and the angles at which they intersect. So when I have two planes of cleavage, it'll look something like that. Okay? In this particular model, there are two planes at 90 degrees. Do you see how they intersect each other at 90 degrees? But wait, Professor Hart, there are four sides to this. What's the deal? Why would I not count that side and that side? Have I said the sides of cleavage, or have I said planes of cleavage? Hold on a second. Hey, Kimberly, what's up? How you doing? Good to see you. I'm teaching. I just wanted to say hi.
Yeah.
Okay. Yes. Yes. Sorry about that. I am in a play this semester, and she is one of my fellow actors. All right. So, where was I? Yes. I'm not counting how many sides of cleavage there are. I'm counting how many planes of cleavage there are. A plane is a surface that goes off along a certain direction, right? Is this plane and that plane not the same? They are. They are parallel to each other. These two sides are parallel to each other, and therefore the same plane. Though they are two different sides, they are the same plane, just on opposites of the mineral. And the same is true for that and this. So though this is a four-sided shape, it only has two planes of cleavage because those two are parallel to the other two. Good, I'm glad that makes sense. And 90 degrees. So if you were looking at a mineral like this, I would say 2 planes of cleavage at 90 degrees. That's it. Now, what does 2 planes of cleavage not at 90 degrees look like? Well, it could look something like this, where I have a cleavage plane here and a cleavage plane here. That's obviously not 90 degrees. That's obviously not 90 degrees. I have 2 planes not at 90, right? It'll break along these 2 planes, but none of the angles of interception are 90. I don't expect you to whip out a protractor and tell me what that angle is. I am not that cruel, okay? All you need to tell me is it at 90 or is it not at 90? 2 planes, not at 90 degrees. Cool? Now, what does 3 planes look like? Well, let's start with 3 planes at 90 degrees. 1, 2, 3. Makes a box. 1, 2, 3 flat surfaces, each of which are intersecting each other at 90 degrees, makes a box. When it breaks into smaller chunks, it breaks into smaller boxes, like that. 3 planes at 90 degrees. Like Minecraft. Ah, yes. Yes. The drug of the generation. I never got involved in Minecraft. I think I was 19 when Minecraft came out or something like that. I don't know. I was a little too old for it. Since you were 5? Yeah, that tracks. Okay, what about 3 planes not at 90 degrees? Well, you'll end up with this, kind of a rhombohedron shape. You still have 1, 2, 3 planes along which your mineral breaks, but none of them intersect each other at 90 degrees. Okay, and when it breaks, you guys just get chunks of smaller rhombohedrons breaking off of that. Okay. Now, what does 4 degrees or 4 planes of cleavage look like? And before you begin to despair, I will not give you anything with more than 4 planes of cleavage. Okay, this is as complicated as it gets. Okay, and it's going to make this sort of shape where you have 1, 2, 3, and 4 planes of cleavage. 8 sides, but that is parallel to this, and this is parallel to that, and that is parallel to this. 4 planes, 8 sides, nowhere along here do they intersect each other at 90 degrees. 4 planes not at 90. We good with this? Any questions about mineral cleavage? Number of cleavage surfaces and the angle. At 90, not at 90. That's it. Okay. Now, what if my mineral doesn't have cleavage? What if it's equally strong in all directions, all of its bonds? What do we have? A circle? Probably not. Besides, I've always found circles kind of pointless. Yeah. What happens if we don't have cleavage? What if my bonds are equally strong in all directions? It might shatter. But whatever, it doesn't have a particular direction along which it will break, does it? We call that fracture. And there are several different types of fracture. Here's an example. This is conchoidal fracture. This is what happens when you break quartz. Quartz, SiO2, 1 silicon, 2 oxygens per bond, a repeating pattern of that, equally strong in all directions. There's no cleavage there. And so it has what is called conchoidal fracture. When you break quartz, it kind of makes this ripply, scooped out look. Okay, there are many other things that do that as well. Glass will sometimes do that if it's been made a certain way. Okay, but quartz will do that all the time because it's equally strong in all directions. Okay, if you pick up any piece of quartz in my classroom and you look for a broken surface, you're going to see conchoidal fracture. That's just one example of fracture, by the way. There are other types. All right, now we already talked about density. We don't really do that here. If any of you get this reference, then your parents raised you well. We already talked about taste. We already talked about texture, smell, Magnetism. Some minerals are in fact magnetic, and you do have a tiny little chunk of a magnet in your mineral test kits, so you can test that. You can see. All right. Effervescence, you have that hydrochloric acid. Please be responsible. Okay. There are more than 4,000 different minerals. We have 8 weeks. Who's ready?
We're gonna study all of them? Or like, at least
No, you're not going to study all of them. I'm kidding. No. At least 2,000. You're ready for 2,000? All right. Angel has volunteered you all for 2,000 minerals. Throw him overboard. No. You only have to know the 51 that I've given you in the practice set. And you only have to identify the 24 I give you in the exercise set. Okay? By the way, when I took this class, there were 250 minerals I needed to know. But that was at a university, and you are in a basics of geology class, and I'm not that mean. And I took out all the ones that you probably won't interact with at any point in your life. The ones I've left in are the ones that are most relevant to people's everyday livelihoods. Okay, the ones that it benefits the average person the most to know. Normal, huh?
what's the rarest one you've seen?
The rarest one I've seen? Cryolite. I believe it's called cryolite. Yeah, I have a sample of it over in one of those drawers from a mine in Greenland that is now tapped out. It's gone. You can't get any more out of that. So I have a piece of it.
What is that material like?
It's kind of like a white, slightly harder than chalk sort of mineral. Yeah. It doesn't look like anything particularly special. If you didn't know what it was, then it might not look special to you at all. Okay, now minerals. We have minerals that we divide into silicates and non-silicates. Okay, a silicate mineral is one that is based around a certain structure, a silicon tetrahedron. Why do silicons and oxygens bond together so easily? There's so much of it, and they bond really easily because silicon has a +4 charge and oxygens have a -2 charge. And so it tends to attract 4 of them to itself and have an overall net -4 charge. The silicon tetrahedron, this is a covalent bond, okay? And you end up with something that looks something like this, okay? Now, because it has a net negative charge, it attracts metals to itself. And the combination of our silicon tetrahedron plus the metals it bonds with, that's the first building blocks of minerals. Silicate minerals are those which are based around a silicon tetrahedron. Non-silicate minerals don't have the silicon tetrahedron at all. We will talk more about silicon tetrahedrons next week. But for now, just recognize these are often the first bonds that form when a magma is cooling down. Okay? So, our silicates tend to form a variety of structures based upon how much energy there is in the system at the time that they form. When you have a high energy system and there's still a lot of motion in your atoms, the more energy your atoms have, the faster they vibrate and the harder it is for them to bond, right? You tend to have your minerals made with independent tetrahedra, silicon tetrahedrons with metals kind of latched onto them. Then as you move through your sequence and things tend to cool off more and more and more, you end up with more complex sequences, ending up with three-dimensional frameworks like quartz and feldspar. Okay? We call that polymerization, by the way, the increasing complexity of the silicon tetrahedron arrangement. Okay? Here's an example of a mineral that's based around one single silicon tetrahedra. Olivine is a mineral. It's this beautiful green mineral over here that I'll show you here in a bit. Okay? Look at that, SiO4. That's our silicon tetrahedron, okay? And it is attracted to ions and 1 magnesium because of its negative charge. This chemical composition makes the mineral olivine. Quartz does not, in fact, have an electrical charge. It is SiO2. Because it is a three-dimensional framework, it has 2 oxygens attached to it instead of 4. And so the net negative charge of the 2 oxygens, -4 charge, cancels out the +4 charge of the silicon. And so they are net neutral, and quartz is itself net neutral. Now, sometimes we will see that some atoms can get swapped out of these atomic arrangements. For example, magnesium and iron are often interchangeable with each other, roughly the same size of atom, plus the fact that they are both +2 charges. And so we'll see magnesiums and irons get swapped out all the time for each other in these compositions. Aluminum and silicon sometimes swap places as well. Okay. Yep. Okay. Let's talk about some of the more common silicate minerals. I got to pick up the pace so you can have plenty of time for lab here. At least an hour for lab, hopefully. Okay. So some common silicate minerals. Okay. Starting up at the top, when things are the hottest, we form our independent silicon tetrahedra-based minerals. These are also called dark silicates. Why? Because they're darker colored. They include lots of irons and magnesiums. Okay, so we've got our olivine, that one I just talked to you about, right? I showed you the example of. And then moving on down into our single chain tetrahedron structures, augite. Then we've got our double chains, like amphibole. Then we've got our sheet structures, which we call micas. And then finally, look at this, by the way, we've moved into lighter silicates. There's no iron or magnesium at play here. This will make a lot more sense when we talk about igneous rocks next week. Okay, but we've moved into feldspar and quartz, our three-dimensional framework minerals. Temperature has decreased to that point. And so we have increased polymerization as heat decreases. So we have our light silicates down here at the bottom and our dark silicates up at the top, also called ferromagnesian and non-ferromagnesian because we like playing with Latin. Okay. So let's start by talking about some of the more common light silicate minerals. Feldspar makes up about 50%. Did you have a question? No. Oh, okay, gotcha. No worries. Makes up about 50% of the total mass of the crust. Extremely common, feldspar. You probably see it every day and you don't even recognize it. Okay. This is feldspar. This is a single crystal of feldspar. Some information about it. It has a hardness of 6. It has 2 planes of cleavage at or near 90 degrees. This is its crystal form. It often grows in these twinned crystal shapes. You can see where they've kind of grown into each other there. We will usually find feldspar crystals like that. It's pretty cool. Okay, I will pass this around here in a minute. I'm just showing it to the camera. Okay, let's start that moving this way. However, what you're looking at is not a broken feldspar crystal, right? So you can clearly see the crystal shape in that. But how are we supposed to tell what the cleavage is? Well, here is a broken feldspar crystal. Same mineral, slightly different color, but the same mineral. And when you look at it, you can see its broken sides, those flat cleavage surfaces that are reflecting light there, they intersect each other at 90 degrees. So we have 2 planes at 90 degrees right here. When you are doing your labs, you may come across a mineral that is not broken enough for you to tell what its cleavage is. If it is so unbroken, you definitely should be able to tell me what the crystal shape is. If you come across a mineral that is very broken, you should be able to tell me what the crystal cleavage or what the mineral cleavage is, even though you can't tell me what the crystal form is. It's perfectly acceptable to say no data for something that you literally can't know. So if you have a super broken mineral, put no data for crystal form. I can't expect you to know that. You can't see it, right? I'd rather you do that than make something up. Deal? Sound good? Great. There are 2 types of feldspars for you to become familiar with. Potassium feldspars and plagioclase feldspars. How do you tell the difference? Well, there are some general color differences. Your plagioclase tend to be on the lighter scale. Your potassiums tend to be kind of that salmon pink, or sometimes they're blue. We call that Amazonite. I have a beautiful chunk of that in my office. Okay. But the best way to tell is to take those cleavage planes and reflect them in the light, because plagioclase will have striations. They are parallel grooves that run in the same direction on your cleavage planes. Only plagioclase will have that. Potassium feldspars will not. And for those of you watching my lab videos online, I take those minerals and I spin them 360 degrees on a lighted surface. Okay? And so you should be able to see. You can just leave things down in that corner in the future, and I'll just pick them up afterward. Thank you, though. You'll be able to see in the videos if the striations are present as the light is reflecting off of that surface. And for those of you here in my classroom, just kind of like tilt it until you see the light on that surface. And if you see those parallel striation grooves, you know you've got plagioclase feldspar. Yeah.
They were like made different.
Yeah. Even though they are both feldspars, they are slightly chemically different to the point that one has slightly different characteristics. And so you could just say feldspar and feldspar, and it would be true. Because these are two different kinds and I'm teaching you how to tell the difference, I do need you to figure out which one they are. Okay? All right. Quartz. Quartz can sometimes appear in dark colors. You can have dark browns, dark grays, dark purples of quartz, but they are still light silicates. Why? Because their chemical structure is still SiO2. Okay? There are no ferromagnesium, there's no iron or magnesium in their structure. So they are not actually no, just here on the table corner. No worries, no worries. Okay. They're not actually chemically different. What happened here is something got stuck in there. Okay. For amethyst, it's purple. There's a little bit of iron stuck in there. It's not part of the chemical composition of the bonds inside of that mineral. For rose quartz, this pink stuff, there's a little potassium stuck in there. Okay. For gray quartz, smoky quartz, it's usually a little bit of uranium that's stuck in there, okay? Whatever the case may be, it doesn't change the fact that the mineral is quartz. When things get stuck in there, we call those inclusions. They tend to color the mineral. Quartz on its own, pure quartz, is pretty transparent. I've got some beautiful samples of that around the room. Pretty transparent. When it has color, it's because it has inclusions. Something got stuck in there. All right, it's disturbing. It's changing the wavelength of the light passing through that mineral, basically. Okay. Quartz has a hardness scale of 7. It's pretty hard. Okay. No cleavage, conchoidal fracture. Muscovite. Muscovite breaks off into those thin leaves. It's got one plane of cleavage. What you're looking at is that's a crystal of muscovite, that's a crystal, that's a crystal, that's a crystal, that's a crystal. There are a bunch of crystals that have intergrown onto each other, but each one has cleavage in one plane, and so it will split apart into thinner and thinner sheets. Ladies, if any of you ever use makeup with glitter in it, it's usually crushed up muscovite. Okay? Yeah, you wear minerals on your face. It's usually what that is. Okay? Pretty cool. Then we've got clay. Clay is often a byproduct of the breakdown of other minerals and rocks. Feldspar, for example, when it breaks down, makes clay. Clay is what we call a secondary mineral. Okay? It is from the breakdown of another mineral. Clay has a lot of uses. We use it to make things like brick, concrete. How many of you enjoy a milkshake? I love a good milkshake. Do you ever wonder how they get it to that consistency where somehow it's not frozen, but it's nice and thick? They add clay. Sorry if that ruins milkshakes for y'all. But yeah, they put a little bit of clay in there because clay is excellent water absorber. So it thickens up that mixture so that they don't have to freeze it, but it also stays thick even though it's not frozen. That's clay. Okay. How many of you are going to go and get a milkshake after this and think, I'm doing homework? Clay. All right. Dark silicates. Let's talk about a few of those. Remember, these are ones that have iron or magnesium, giving them that darker colors, usually greens or blacks. Okay. Olivine. Olivine is the green mineral that you see in this rock. This is called peridotite. Most of the mantle is made out of this. Underneath of the crust looks like that. Isn't that gorgeous? I think peridotite's probably one of the prettiest rocks. Oh, come on, camera. Stay with me here. Probably one of the prettiest rock types. Come on. Look at me. Over here. You can do it. Let's try that again. It wants me to stand further back. Over here. You want me to use my right hand? What is going on here? All right. I'm just going to have to stand in front of the camera for the moment. I'll figure that out in just a second. It might have zoomed in on me at some point. Okay. So we've got these green crystals. That's olivine. The black ones, that's pyroxene, which we'll talk about here in a minute. But most of those are green. That's olivine. Beautiful, beautiful color. Okay. Conchoidal fracture, hardness of 7. Okay. Olivine is actually one of the first minerals that ever forms in a magma. Iron and magnesium. Yep. It is a dark silicate. Okay, let's see what's going on here with my camera. Look at me. There we go. It's a what? Thank you. I like it. Okay. I'm a walker. Well, in case you haven't been able to tell. Yeah, so I needed something to follow me around. Okay. Next up, we've got pyroxene, which are the black crystals that you see in that sample getting passed around with the green ones, okay? Pyroxene has 2 directions of cleavage at 90 degrees. It is black. It is opaque. It is the most common ingredient in igneous rocks like basalt, which we will learn about next week, okay? Now, pyroxene and the next mineral are often confused with each other. Some of you will probably confuse them with each other on the lab, but let me tell you, the best way to tell them apart is the cleavage. They look very similar, and they have very similar colors until you look at the cleavage. Where pyroxene has cleavage in 2 directions at 90 degrees, amphibole here has 2 directions not at 90 degrees. And it will be pretty obvious once you look for it, okay? Color, crystal shape, all of that, they'll look very similar until you look at the cleavage. That's the best way to tell them apart, okay? Then we've got biotite. Biotite is the ferromagnesian version of muscovite. That one I say we grind up and gets put into makeup, okay? It's the ferromagnesian version of that, okay? So it's got irons and magnesiums in there. It still has the same cleavage, usually forms in very similar shapes, but it's just got the iron and magnesium in there instead, okay? And then we've got garnet. Garnet is interesting because it appears in both igneous rock and metamorphic rock. I think of garnet as kind of like a trash can mineral because you can make different kinds of garnets based on a whole bunch of random stuff that's in there. Garnets often will form out of just whatever's in the rock. Okay, like in metamorphic rock, you start to form a whole different new rock, and your garnet kind of sometimes forms out of whatever's left over after the fact. It's kind of why I call it a trash can mineral. It may not be entirely justified, but that's just how I think of it. Okay, no cleavage. These are hard enough that they're often used as commercial abrasives. Okay, and then we've got our non-silicates. Non-silicates represent only about 8% or so of minerals on Earth. Most of the minerals here on Earth are, or at least in the crust, are in fact silicate minerals. The other 8%, non-silicate. So what I mean by non-silicates, they don't use the silicon tetrahedron. Instead, we group them based on what oxides, or not oxides, what ions they have in common, okay? So for example, our carbonates, calcite and dolomite. Our oxides, hematite, magnetite, corundum. You may also know corundum as ruby and sapphire, okay? Ice is an oxide because it has that O2 negative ion in common with the other ones, okay? Then we've got our native elements, gold, copper, diamond, sulfur, all the things that show up as individual. They are simply conglomerations of a single atom, or a single element, I should say. Gold is nothing but the element gold, right? A whole bunch of atoms of the element gold. Same thing for diamond. It's a whole bunch of atoms of the element carbon, right? Those are native elements. That's what we call those. Now let's talk for just a minute about mining, okay? Mining is how we get all these valuable materials out of the ground. Oftentimes, we are seeking the highest concentrations of some particular element, be that gold or magnesium, okay, whatever it is, we want something, and so we are going to target the places and the materials that have the most of that something. That is mining. Now, mining is a tricky prospect because you have to be able to get your target material out of the ground while doing it at a cheap enough cost that you are making money. We call the material in the ground that contains what we are looking for, we call that ore. That's what ore means, okay? I used to work at a gold mine in Nevada. I was working as an exploration geologist at a gold mine in Nevada, okay? And basically what I would do all day is I would just hike. When I wasn't writing reports or doing things in the lab, I would go out and I would hike in places that the mine was considering purchasing for the mineral rights. I just go and I collect samples, pick that up, pick this up, pick that up, pick this up, make sure I label them so I know where they came from. Then I go back to the lab and the metallurgist would grind it, crush it down, and then do a test to see exactly how much gold was dispersed in that rock. If it was anything less than 0.03% parts per million, we had nothing to do with it. More than 0.03 parts per million, that was viable. We could make money off of that little gold in a rock. I mean, that's like hundreds of tons of rock to get 1 ounce of gold out. But at the scale that we were working at in this mine, we could make money off of that, okay? And so if it was worthwhile enough, if the concentration was high enough, yeah, they would build a new pit there, okay? I worked at an open pit mine. The concept is true for underground mining as well. This is what an open pit mine looks like. This is the Bingham Canyon copper mine. If you're having a hard time figuring out the scale there, then yes, those are mountains behind it. Okay, that's the sort of scale we're looking at here. The haul trucks that I worked with, I never drove them. I got to ride in them a few times, but I was driving around them all the time. If you've ever never seen a full-scale, full-size mining haul truck, they're crazy. The cab of the truck is about this height off the ground, where we are right now, looking out at the parking lot.
There's no part that's a climb?
Yeah, the tires of the truck were from floor to ceiling in height. And there were 2, 4, 6, 8, 16 tires on each truck. Each truck was capable of hauling 500 tons, I believe. Yes. Yeah, I should dig up a picture sometime of me with one of those haul trucks. It's incredible.
I think I've seen it compared to like a bus, just like a regular bus.
Yeah. Yep. You could probably fit a bus inside of the bed. It might stick out the other end, but I mean, you could carry a bus with absolutely no problem. Okay. Now, let me delve a little bit more into why the economics of a mine is so important. This is the Bingham Canyon copper mine. A while back, I believe it was during the 80s, China started producing lots of copper and throwing it out on the market for dirt cheap. They will do that every now and then, okay? it's an attempt to try and take over a market. If they can saturate the market with their product, make it really cheap, and drive out of business any of their competitors, then when all their competitors are dead or bought out, they can increase the price to whatever they want and be uncontested. Yes, they do that all the time. There's an interesting intersection between geology and economics for you. Okay, Bingham Canyon faced a tough question. Do we invest hundreds of millions of dollars into revamping our infrastructure so it's more efficient to generate copper, or do we sell while we still have possibly some money left, where we can still pay our employees? They decided the first option. They invested in remaking their infrastructure, revamping it, so it was much more efficient. And they were able to match Chinese market prices. And it's a good thing for us that they did, because they are still producing copper and we don't have to buy all our copper from the Chinese. Imagine how different our technological progress would have gone in the last 30 to 40 years if we hadn't had a steady supply of copper here locally, right? The world could be a very different place, let alone the United States. There are 17 elements down here, these ones, which we call rare earth elements, okay? Rare earth elements are those which are so widely dispersed, like there's so little of them in any particular sample of rock that it takes a lot of time to refine them out of it. And so if you find a place that is rich in those things, and when I say rich, I mean very, very low amounts by any other standard of any other mineral, but still rich because they are that rare, then you set up a mine there and you start mining it, because these are elements, say, terbium, right here. Terbium, that's a rare earth element. Some of these things like terbium, you use in complex electronics. Everything from your cell phone to your Xbox to night vision goggles and Tomahawk missiles for the military. Anything that requires advanced electronics uses some of at least one rare earth element. It's required for our current technological state. Due to several very savvy economic choices, China currently holds the market on about 98% of all rare earth elements. They produce that much. Anytime any other country tries opening another rare earth element mine, because the prices are so high they can, China drops the prices so it no longer becomes economically viable to start another mine. They have the rest of us firmly like that. Okay? And all they have to do is turn off the faucet. If someone pisses them off, you don't get any rare earth elements. 8, 10 years later, once all the technology we've had before has fallen to the wayside, has fallen behind everyone else, that country becomes crippled. It's one of the reasons why people really, really don't want to risk messing with China. One of the reasons that hardly anyone knows about, right? Okay. Any questions about anything we've talked about today? No? Let's move into lab time. You do have a lab PowerPoint, but it basically just goes into all the same things that I already talked about. It's just kind of there for you to use as a quick resource, with the exception of a few things. There are a few things in that lab PowerPoint that I want to point out. Give me a second and then I'll pass out the lab sets. Okay, so when you go down through these, oh, this is funny. Have any of you ever seen Journey to the Center of the Earth with Brendan Fraser? Yeah? There's a part, Brendan Fraser plays a geologist, and he's going down through this volcano with his son and a cave guide, okay? And they've gone their way through this whole volcano and they enter this room full of jewels. Okay, see if is my volume up on this. It's just a funny little clip. Yeah.
Rubies. Emeralds.
Feldspar.
Hopefully by now you understand why that's funny. The two non-geologists were like, "Oh, look at these jewels," and the geologists were like, "Oh, look at this feldspar. You know, 50% of my planet's made out of this, but oh, feldspar. That's geologists for you." All right. So all our physical properties, yada yada. Here are some examples of what some of the shapes, the crystal shapes you could be looking at are. However, I strongly encourage you to use this website. Okay, this is on slide 5 of the Lab 1 PowerPoint. Use that website. It has rotating views of all the possible crystal shapes you could be looking at. Basically, if you want to identify it, count the number of unbroken sides, flat surfaces, like we saw on this feldspar crystal, right? You would count the number of unbroken surfaces there, and then you would go to the appropriate place on this website. Say you count 6, okay? Go to the 6-sided shapes, okay, which one of these shapes matches most closely what I'm looking at? And there's your answer. Remember, if it's too broken, you won't be able to tell crystal form. But then we've got cleavage. If it's very broken, you definitely should be able to tell me what the cleavage is, right? But you count the number of broken but flat surfaces and what they intersect at, what angles. Hardness, we already talked about that. We already talked about color. We already talked about streak. We talked about luster. Here are some physical examples of what lusters could look like. This is vitreous or glassy. Then you've got pearly, right? Resinous, that kind of looks like dried tree sap, for lack of a better term. Silky, it just kind of has that sort of silky sheen to it. Greasy, like someone sprayed it with cooking spray, right? Earthy, looks like dried mud or sand or something, okay? You've got your different tenacities we talked about, your optical properties, a few other things. I give you this flow chart to give you an idea of the best way to go through this. I recommend collecting all your properties first before you try identifying it. Collect all your properties, and then just starting at the top, go through the process of elimination. I'm looking for something with this crystal form. Anything that is not that crystal form is eliminated. I am now looking for something with that crystal form and also this many planes of cleavage at this number of degrees. Everything else, eliminated. Okay? Just kind of work through it like a flow chart, process of elimination. Now, I provide for you a very valuable resource called the Lab Excel spreadsheet. Okay? It's on Blackboard. I don't have it on my hard drive. It's a living document. I update it. It's on Blackboard, so you can open it from Blackboard. It's also on the class website. Okay? That is going to be your best friend doing these labs, because on that Excel spreadsheet, it's a catalog of all the 51 practice minerals, every property that they have, and pictures to go with it. And it goes hand in hand with the YouTube videos that I've made on my YouTube channel that show all the videos of me doing these tests myself. For those of you in this classroom, I encourage you to do it yourself. For those online, use my videos, okay? But that in either case, online or in person, that Excel spreadsheet is going to be your best friend for this lab, okay? After you find your properties, you're basically just, it's a game of match. If you've collected your properties correctly, it should, or most of them, should match with something on that spreadsheet. Cool? And then you just fill in the blanks on the lab assignment on Blackboard. Cool? By the way, when you do find the right match, if you find a few things didn't quite match, like if you said it was gray, but the color is actually black on the Excel spreadsheet, don't change your answer to match that. I want you to keep your authentic answers, because if for some reason you do get it wrong, I want to be able to see where you went wrong. Does that make sense? Keep your answers on there. Any questions about Lab 1? All right, well then I'm going to end the recording here and pass out the samples.